Okay, welcome back. So we've talked now about vector graphics and this problem we need to eventually move to rasterizing. We haven't talked about how to do that yet, but that's a bit of a slow process, unfortunately. But I want to talk about one more thing, and that is the data in a raster. We haven't covered that. We've talked about the fact that color uses an RGB model and why. We've talked about that a raster is a grid of pixels, but what do we store? What do we store in each pixel? So each pixel on a raster, we need to put some data in there. What is it? Of course, is represented by bits. So for example, the base case could be 1 bit. 1 bit per pixel. And if you go back and look at the slides from last unit, you'll see we actually had an example of a font that uses this. Now, if we have 1 bit per pixel, then each pixel is either on or off. These are classic black and white displays would sometimes do this, where it's either on, it's off, the gun hits it or it doesn't. Great, very basic. Now we can also have 4 bits per pixel, 4 bits per pixel. And so if you imagine that because I have 4 bits, I have 2 to the 4 possible values in that pixel, which is 16 values. 16 values. I'm going to move this to the left a bit so I have room. Let's do that. Look at that, hey? Digital. Gotta love it. Graphics, right? Gotta love it. So that's 4 bits per pixel. If I have 8 bits, whoops. If I have 8 bits, then of course I have 2 to the 8, which you should all know is 256 values. Now I'm going to take a stop here before we go into the higher bits and talk about how this worked. So when I was a kid, 4-bit and 8-bit graphics was very common, and I programmed these and I learned how they work. But what do you do with 16 values? What do you do with 256 values? Now I was very lucky to have a color monitor growing up. I had a VGA monitor which could do a lot of different colors, but my memory was limited to 8 bits a pixel. So this is what we did. These things used a strategy called a color palette. To represent the colors. So these palettes, you'll still come across them. Okay, you still come across them from time to time. And what a palette is in terms of computer graphics is it's a lookup table. Okay, a lookup table. And I always like to envision an actual artist's palette, and I can't do a good job drawing it. And you have all these paint that you put in your palette. But look, my palette only has 7 spots. This is spot 0, 1, all the way up to 1, 0, 1, 2, 3, 4, 5, all the way up, right? I have 7 spots, and I can load colors into those spots. So a palette was a lookup table that indexes raster pixel values, like 0 or 4, right, to an RGB intensities. Now, I'm really not going to bore you with a lot of history here, but in the very early days, we had a system called CGA and EGA. Again, this is from when I was a kid. These had 4 colors and 16 colors, and the video cards came preloaded with your colors. Stupid idea. So it had these 4 colors, and all your programs could only use these 4 colors, or these 16 colors could only use all 16 colors. And the reason this is a stupid idea is because the monitor itself is capable of varying the intensity of that ray, right? It's capable of varying that intensity a lot more smoothly than just a few values. So then when VGA came out, which was a better graphics card, VGA had 256 8-bit color, but it didn't have a preloaded palette. You could program this lookup table. So you had a programmable palette. Now the difference would be here, either you're given a palette, you have 4 colors, you can use them, or you can put whatever colors you want on that palette. So that was very exciting, and you can choose R, G, and B intensities and put them on the palette, and you can use those 256 colors. Don't memorize this. We're not going to test you on your knowledge of this, but it's very useful history, and it does come up from time to time. If you're into retro gaming, or if you find yourself working on an archaic system for tractors, it might say, okay, you have an 8-bit palette. Oh, okay, because it's cheaper to have that device. So it's useful to have that scrolled away in the back of your head. So a palette's a lookup table, and yeah, it would kind of look like this. Whoops, let's try to fix that. There we go. A palette might look, come on, Apple. Don't you know that's my hand? Okay. Yeah, and I'm not going to edit that out of the video. Sorry. So my palette might look something like this, where I have 0, 1, 2, all the way down to 255, right? 256 values, and it would point to an R, G, and a B value. So one might be 0, 0, 1, which is blue. This one might be 0, 0, 0.5, which is a different blue. This one might be 0.25, 0, and then 0, which is a little dark red, and so on and so forth. So you could program these palettes. So the nice thing about these palettes was you had low pixel bit depth. So each pixel didn't take much memory. So you have low pixel bit depth. Less memory. You might think, who cares about memory? Memory's free. Well, it's not if you're on an embedded system. It's also faster. Why? Because you're moving less memory around. Okay? So lower pixel bit depth, it's great, it's faster, but as you've seen with our palette idea, it's less flexible. Okay, so I'm going to continue this. I'm going to grab a highlighter. I'm going to continue this thought process. So after 8 bits per pixel, another standard is 12 bits per pixel. Now, as we increase the bits, we moved away from the palette and we moved to RGB type color. So these 12 bits, we'd actually have 4 bits for red, 4 bits for green, and 4 bits for blue. That's my 12 bits. And now I can have intensity. Of course, 2 to the 4 means I have 16 values, 16 levels of intensity. Right? So I can have red, green, and blue different intensities. I actually get, 2 to the 12 is a lot of different colors. This starts getting really useful. And then we have the now ubiquitous 24-bit color, which is same thing, except your red, green, and blue have 8 bits per pixel. Okay, 8 bits per pixel, where 2 to the 8 is 256 values. And if I take 2 to the 24, which is all my bits here, I have roughly 16 million colors. Okay, that's pretty much what we'll see now all the time. Okay, you're not going to find computer screens that want much more color than that. The only times you'll see more bits per pixel is if you're into professional photography, and it's not because it looks better, not at all. No, your eyes can't see more. You can't differentiate beyond this. It's useless. So why do we use it in photography? Because it gives you more room to process it. You can brighten it up and stretch out that color gradient. And if I stretch it out 3 times, if I have higher bit depth in my color, I can still not see the variance. If I take this 8-bit and I stretch it out, suddenly I might have only 15 values between black and red left after I stretch it out, after I modify that picture. So just like with audio, people record at ridiculously high sample rates so that you can process it and not ruin your audio. The same thing with video. Your expensive cameras have higher bit depth only because it lets you process it better, not because people can see it better. Okay. Now, where am I? Yeah, and with these ones here, and woohoo, let's undo that. With these ones here, as I said, instead of using palettes, I said this, but I should write it in my notes. Instead of using a palette, just put full color value in each pixel. So you don't need a palette anymore. You just put the value you want, red, green, and blue, right in that pixel, because now we have enough memory. Of course, more memory, right? Which means slower, but flexible. I'm not sure how much it matters now, but going back about 8 years or 10 years, I actually had to convert one of my projects from 24-bit to 12-bit color because it was too slow, and I needed just an extra bit of speed out of my bandwidth. So you might still find yourself coming across these kinds of situations. Now, there's something that some of you might be noticing, especially if you've done operating systems and comp org and those kinds of classes. 12-bit, 24-bit, those are nasty numbers. Those aren't good numbers for computer scientists, because these are not multiples of 8, right? And if I have a 32-bit machine, I have a 24-bit number, you pack them, you gotta do ands and ors, you gotta unpack them. It's not just, you're not following the byte boundary or the word boundary. So that's a hassle. We have byte and word boundaries that you should know from other classes. So sometimes people just convert them. Yeah, I know it's 12-bit, I'm just going to use 16 bits. I know it's 24-bit, I'm just going to use 32 bits. I don't lose anything. Because of these byte boundaries, I'm already having to pad it or process it. I'll just use a little more memory, and it doesn't bother me. The little more memory doesn't bother me because I'm gaining in speed, not having to process those pixels and funny boundaries. So this is, you might notice, is 2 bytes, and this is 4 bytes, which is nice, right? If you have a 32-bit machine, bam, that's a word size right there. Now, another thing that you'll see people do with this is they'll put the red, green, blue, and well, look, we have these 8 bits left over. What do we do with them? You'll see them do A for alpha. Alpha is, I should write that down. Alpha. The alpha channel used for transparency. See-through. So if I specify something as 100% see-through, the pixel's useless. If I specify it as 50% see-through, then the program rendering it, if you're drawing on top of something else, it should blend them together for you. I'm not going to get into blending right now, in this course rather, but I wanted to highlight this this 8-bit alpha that is built into the 32-bit color mode. So let's see if I'll give you a quick demo. Where are we? Okay, here we go. So here's an example. We have this smoke here. We have this smoke here. You can imagine having this as one graphic with an alpha built in, so it sees through, and you just draw it on top of this picture of an alley, and it looks see-through. The computer blends them together using an algorithm. Now I'm going to try see if I can do a live demo of this. This is the GIMP. I'll zoom in a moment because you obviously can't see this. I'm going to load up this file that I found on the internet. This is not it. This is a processing file. Let's go to the right folder and grab the right file. That'll do it. Cool. So here's a there we go, I'm in the GIMP. Here's a picture of a fire. You see this checker box background? That's not actually part of the picture. This is something that programs like the GIMP do to show you. See, it's not zooming in. It's staying the same size. It's showing me that's alpha. That's see-through. Here, there's no see-through. So I can zoom in and see all my pixels. It's a raster. Cool. It's not a vector graphic. And on the edge here, you can start to see where you have this alpha value. Now, I'm going to choose my color picker, and let's see how well this works. Okay, you can't really read that. Let's see. I'm going to pause this. There we go. Ta-da, ta-da. I hope this is working. Okay. So here's my color picker, and I can click on a pixel. Here we go. And I have a red 100% or 255, 8-bit per channel, 8 bits for red. Look at that, red, green, and blue, and alpha is 255, so there's no see-throughness here. But look at this one, I can see pixels. Click. Alpha's 219, I click over here. Alpha's 208. So this is really cool. I click here, alpha's 174, all the way down to 14. So the alpha channel shows how this fades out over time. So that's really cool. And you can see that red, green, and blue, 8 bits per pixel, and we have the alpha channel right there. Okay, I actually paused my video for a second to grab another image to better demonstrate this. So I've added another layer to this file so I can superimpose the fire on top of something. So let's say I wanted to burn something. I can now put this fire right on top of another picture, and if I zoom in here, you can see where that alpha is. It actually smoothly, overlays, right? That alpha channel blends in. So those pixels are used for transparency. Cool. All right, so let's take a break here. I'll come back and we'll get more into rasterization.